Hello guys, today I am going to discuss a very important type of spectroscopy, that is UV and visible spectroscopy. And as always, I am not concerned about the instrumentation itself, but I am concerned about basic principle, basic concepts, factors which are affecting this kind of analysis, as well as a great detail of examples. So without wasting time, let's start guys. In ultraviolet or visible region, the light is of 200 to 400 nanometer, that is UV light, and 400 to 700 nanometer, that is visible light. Now in a test tube, if we are having organic molecules and we are putting the UV or visible light on these organic molecules, what kind of interaction we get? The interaction is generally electronic transitions. Electronic transitions means these organic molecules can absorb the light in UV and visible region and can show electronic transition means electron can go from lower energy state to higher energy state, or in other terms ground state to excited state. So if we go in little bit detail, then we find that according to molecular orbital theory, for a molecule you are having two types of energy orbitals: high energy orbitals or low energy orbitals. Low energy orbitals can be called as ground state as well as HOMO, highest occupied molecular orbital. So for example, then in this case in HOMO we are having two electrons which are having opposite spin, and the same molecule is having high energy orbital or LUMO, that is lowest occupied molecular orbital, or in other terms it is called as excited state. We already know that there will be some energy difference between ground state and an excited state, and that energy difference can be covered by the electron after absorbing the UV light between 200 to 400 nanometer and visible light between 400 to 700 nanometers. So principle is very simple. You are having ground state and excited state. Generally your electrons are present in the lowest energy possible, that is ground state, and they absorb the light from UV and visible region and they will go to excited state. So one of the electron has transferred or transitioned to excited state. It's very simple. Now if the electron is absorbing the light, then obviously we will get the spectrum. So in this particular example, our molecule is absorbing the wavelength of 360 nanometer as well as wavelength of 443, 471 and 502 nanometer. So at these particular wavelengths, it is showing electronic transitions between ground state and excited state. So on x-axis it will be always wavelength in nanometer, and on y-axis it will be absorbance. Now we see how the organic molecules are interacting with UV visible light with different examples, and we try to understand which kind of spectrum we are going to get. So for example, if we take hydrogen gas. So hydrogen gas or H2 is having single bond, and both the electrons in this molecule are present in sigma HOMO orbital or the ground state, and the excited state is sigma star, that is our excited state LUMO. The energy difference between this ground state and excited state is 258 kilocalorie per mole, and this kind of energy gap can be covered by UV light absorption of 111 nanometer. So after absorbing 111 nanometer, one of the electron is going from ground state to excited state. It's very simple to explain. Now the problem is, generally the UV visible light spectrometers which we are having, they show or they analyze the spectrum after the wavelength mark of, you can say, 240 nanometer. So it is very difficult task to analyze the absorption at 111 nanometer. So we somehow call the hydrogen molecule as UV visible inactive molecule. Means it is very difficult to observe the UV visible spectrum for hydrogen gas, or you can say for single bond because the energy between the ground state and excited state of a single bond is very high, and since the energy gap is high, you will be absorbing, or the molecule will be absorbing, the UV light of very less wavelength, and this much less wavelength spectrum cannot be analyzed by currently present UV visible spectrometer. So a single bonded molecule, it is difficult to analyze by UV visible spectroscopy. Now we move to a double bonded molecule. So a double bonded molecule, CH2 double bond CH2. We are bringing the pi orbitals because now the double bond is there. So the gap between ground state and excited state is 173 kilocalorie per mole, and that can be crossed by absorbing the UV light of 165 nanometer. So you can say after 165 nanometer, the electron is going from pi to pi star, or it is going from ground state to excited state. Now again the problem is, it is still not reaching to 240 nanometer. So till now I can say single bond, it is difficult to analyze, and double bond, still it is difficult to analyze. So we move to another system which is containing two double bonds, and these two double bonds are present in a resonating or conjugating system, that is double, single, double bond. So you can see in the energy diagram that ground state and excited state now having the gap of 130 kilocalorie per mole, means the gap is getting narrowed down, or it is getting shortened. Since the gap is less, it is crossed by absorbing the wavelength of 270 nanometer. So after 270 nanometer absorption, your electron can go from ground state to excited state, and you can get a spectrum. Now we are reaching to our range, but still it is not enough. We have to go to 240 or beyond that. So what can we do? So till now logically we can think that single bond, energy gap was high, one double bond, it is little bit less, two double bond in a conjugated system, it is getting lesser. So if I increase the number of double bond in a conjugated system, I will reach to my range. I will cross the range of 240 nanometers. So we see the example, double, single, double, single, double, three double bonds and in a conjugated system, and now the energy gap is very less, that is 111 kilocalorie per mole, and this energy gap, the smaller energy gap, can be crossed by absorbing the UV light of 258 nanometer. I have reached to my region. Now I will start observing the UV visible spectrum. So it is very clear till now that double bonds are somehow necessary because they are having smaller energy gap, and conjugated double bond system, it will be very easier to analyze because energy gap will be much lesser, and you will be having your range which is more than 240 nanometer absorption, and you will start having UV visible light spectrum. So maybe in next examples, if we are increasing the number of double bond, we are creating a great conjugated system, the energy gap will be so less that it can be crossed by just absorbing the light in visible region. So we'll see different example. Now we move to another example, right? So here we are having a double bond, then we are having single bond, then we are having double bond. So double bonds are arranged in a conjugated fashion, and the molecule is having lone pair also. Now the example is getting very interesting. So we will be getting two peaks, one for the double bond transition and second for the transition of lone pair. So that is shown here, n2 pi star. So the gap between lone pair and the higher energy state is very less. So the wavelength has increased, that is 314 nanometer. So we are going to get two peaks, one for double bond, one for lone pair, and those two peaks will be highly visible for us. And the interesting part, the best part is, now we have understood we need a conjugated system, as well as if we are getting lone pair, it is easy to show the UV visible light spectrum, right? So what we look in a UV visible spectra. So we put our sample and we put a light of a particular intensity, that is I0. The sample will absorb some light and remaining light will come out, that is I. So we are having a term which is given by Lambert Law, that is log I0 upon I, that is absorbance. So absorbance is giving you the amount of light absorbed. And the second term for the UV visible spectra is lambda maximum. Lambda maximum is that wavelength where the absorbance is maximum. So as we have seen one example, that one organic molecule is absorbing the light at 258 nanometer. So we'll be getting maximum absorbance to that particular wavelength. So absorbance will be given on the y-axis and lambda maximum will get by the x-axis. So it is very simple. Now we go to the biological example where we understand the UV visible spectra of ATP. So if I look the structure of ATP, I find there is a conjugated ring system, and conjugated ring system is giving us the absorbance at nearly 254 to 260 nanometer, that is the lambda maximum of ATP, and on y-axis I am having the absorbance. So this is the UV visible spectra of ATP. Very nice spectra. We are getting very good peak in the UV region near 260. So this peak is coming because of this conjugated system of adenine. So it's a well-known fact that DNA is also having its absorption at 254 nanometer. That is because it is containing nitrogenous bases which are showing or which are having conjugated ring system. So the wavelength of ATP, wavelength absorption by the ATP is nearly similar to DNA, because both of them, they are absorbing the light because presence of nitrogenous base. So it is very simple to show. Now in a test tube, if we are having a test tube full of ATP and we want to check whether the ATPs are present or not, then we just put UV light range and then we get to know, okay, at 260 nanometer or between 254 to 260 nanometer we are having absorption, that is our lambda maximum, and we say okay, ATPs are present or DNA is present, right? We see another example which is a very important molecule in biological system, that is NAD plus and NADH. Now why this example is important? Because doing UV visible spectroscopy of NAD plus and NADH is very important to learn about so many different types of metabolic pathways. So I give you the example. So this is the structure of NAD plus. So in NAD plus we are having a conjugated system here in the form of this ring, and this ring is containing a positively charged nitrogen. And if I look at the spectra of NAD plus, then I find that we are having lambda maximum nearly 250 nanometer. At 250 nanometer it is giving a good peak, right? Now in metabolic pathways, when it converts into NADH, then what we are getting, when it is converting into NADH, then nitrogen is losing its positive charge and it is having a lone pair. And we have seen that once the lone pair is coming, then energy gap is getting down and the molecules start absorbing at higher wavelength. So you can see in NADH we are getting two peaks, one similar to NAD plus at 258 nanometer, and second peak we are getting nearly 348 or 350 nanometer, which is a very interesting example. So in a biochemical reaction, if the oxidation is occurring, then it is accompanied by reduction of NAD plus to NADH, that is acceptance of electron by NAD plus. So if NAD plus is getting reduced into NADH, then we will be getting two peaks, one at 250 nanometer and one at nearly 350 nanometer, and we will be saying okay, the molecule is present in its reduced form. It means the biochemical reaction is a oxidation reaction, right? If the biochemical reaction is a reduction reaction, then in that case that will be accompanied by oxidation of NADH to NAD plus, and in that case the peak of 350 nanometer or nearly 350 nanometer will vanish. So if we are getting two peaks, then in the system oxidation is occurring and NAD plus is converting into NADH. And if we are getting only one peak or majority peak is the single peak, then we say in the test tube reduction reaction is occurring, that is why NADH is converting into NAD plus. And by looking at the ratio of these peaks, we can say how much oxidation and reduction is occurring. So it is a very important technique to understand the redox reaction in the biological system just by looking at the peaks or lambda maximum of NAD plus and NADH. So I hope you understood the example. We move to another example, that is another oxidation reduction system, that is cytochrome C. So cytochrome C is the molecule present in electron transport system, and it can be also present in two forms, reduced form and reduced form and oxidized form. So this oxidized form of cytochrome C is having one major peak, nearly 400 nanometer, and once it is getting reduced by accepting the electron from complex 1, then complex 1 2 electrons are going to complex 3, and cytochrome C is the part of complex 3, and after getting reduction or after getting reduced, we are having new peaks at 400 as oxidized cytochrome C, then after 500 and around 550 or so. So presence of these three peaks is giving us the idea, okay, cytochrome C is in reduced state, and presence of only one peak is giving us the idea, okay, cytochrome C is present in the oxidized state. So all the components of the electron transport system are discovered like this only. So we can check their oxidized state as well as their reduced state, right? Now we move ahead to another biological example, that is beta-carotene. So the color of beta-carotene is orange, and what is the reason behind that? You can see the structure of beta-carotene. It is having so many double bonds, and all of them are present in conjugated fashion, that double bond, single bond, double, single, double, single, double, single. And we know that if we increase the number of conjugated double bonds, then energy gap gets down, and once the energy gap is less, we get absorption in higher wavelength region. And you can see that beta carotene is absorbing the light between 400 to 500, and that is the visible region. So it is absorbing light in visible region, and the orange light, you can say, it is transmitted through the molecule. That is why beta carotene is orange in color. So it is a pigment of plants which is absorbing light in visible region because it is having a long conjugated double bond system, and which is proving the theory that double bonds are important, conjugated systems are important to do UV visible spectroscopy. Now we move to UV visible spectroscopy of proteins. So in proteins you are having two types of major types of bonding. One is peptide bond, and we can see that peptide bond is showing the absorbance near the wavelength of 220 nanometer, and the major absorption for protein comes because of presence of aromatic amino acid. Aromatic amino acid means you are having conjugated system, and they show the lambda maximum in the higher wavelength region, and you can see that 280 nanometer is their favorite lambda maximum. So now we know that DNA is having the maximum absorbance at 254 nanometer, and the proteins are having maximum absorbance at 218 nanometer, and the aromatic amino acid means phenylalanine, tyrosine, and all these guys. Okay, so by looking at the ratio of 280 nanometer and 254 nanometer, people check the purity of protein or purity of DNA. We will see the example in next one or two slides. So we now know the UV visible spectroscopy of ATP, DNA, and NAD plus, NADH, oxidized state of the molecule, reduced state of the molecule, beta carotene. So we move to next example where we are understanding the behavior of DNA with increasing temperature. So it is our double stranded DNA, okay, and we know that the absorbance of DNA is nearly 260 nanometer, 254 to be precise. So in this graph we are having temperature, and 260 nanometer absorbance on y-axis. So if the temperature is less, then DNA is present in form of double-stranded DNA, and if you increase the temperature, you start melting the DNA, you start breaking the hydrogen bonding, the triple hydrogen bonding between GC and double hydrogen bonding between A and T. So what is happening, once the DNA is getting melted, then absorption is increasing because now the bases are free. They can absorb more light at 260 nanometer. So you can see double stranded DNA is here in the graph, then melted DNA is here, then finally you are having single stranded DNA. So you are creating a graph where you are showing the effect of temperature on the absorbance of DNA, and the midpoint of this graph is denoted as the melting point of DNA. So by doing UV visible spectroscopy in increasing temperature condition, you can find out the melting point of DNA just by saying double stranded DNA less absorbance on 260 nanometer, melted DNA more absorbance at 260 nanometer. So the midpoint of that graph on x-axis is giving you the information about melting temperature of DNA, and it is very important because whenever we do PCR, we have to design primers, and for primers melting point is very important to decide annealing temperature in PCR, and for that we should have the information about melting point and GC content. All of them, they can be analyzed by doing UV visible spectroscopy in increasing temperature conditions, right? So one more example I will do. So I have told you that the DNA is absorbing the light at lambda maximum of 260 nanometer, and protein is absorbing the light at lambda maximum of 280 nanometer. And if in a mixture we are having both protein and DNA, then we can find out the percentage of the DNA and protein, or the purity of DNA and protein. So we are having different conditions where we are having 100% DNA, then 60% DNA, 40% protein, then 40% DNA, 60% protein. So we are going from 100% DNA and we are starting having increasing percentage of protein, and ultimately we are having 100% protein and 0% DNA. So you can see the first blue line. So you can say, okay, protein is absent. So protein is absent, so we are not getting any peak for the peptide bond, and maximum peak we are getting at 260 nanometer, right? And in the last line where 100% protein is present, then we are having very good peak for the peptide bond, as well as we are having very good peak at the 280 nanometer. So in the experiment where you are increasing the protein, so you are shifting your lambda maximum from 260 to 280 with increasing concentration of protein. So the ratio of absorbance at 260 to 280 gives you the purity of DNA in a sample, or vice versa. You can check the purity of protein in a given sample just by making this graph. So in the complete graph, when you are increasing the amount of protein, then the peak at 260 is decreasing and the peak at 280 is increasing, and similar result you are getting for the peptide bond nearly 220 nanometers. So I have given you so many examples of biological importance, and we have also understood the importance of double bond and conjugated system in UV visible spectroscopy. So I hope you understand the complete topic, and if you are having any doubt or any query, you can always write to me at logicalbiology8484@gmail.com. So the last topic, which is the Beard Lambert law. So generally people explain it initially, but it's very simple. You are having I0 light, then you are putting that into sample, and you are having I light coming out, and log I0 to I is your absorbance, and that is equal to epsilon C and L. Epsilon is the I0 is the intensity of incident light, I is the intensity of emitted light, and A is absorbance, and epsilon is molar extinction coefficient, which is another important parameter to understand UV visible spectroscopy. L is the path length, or the length of the sample where the light is passing through, and finally C is the concentration. But the aim of this video was to tell you what are the factors affecting the UV visible spectroscopy and what are the biological examples, because ultimately what I think that for a biology student it is very important to understand the examples of a technique and how they can apply. So in my lab tomorrow, if I am trying to find out the the conversion of lactate to pyruvate or pyruvate to lactate, for me that is the oxidation reduction reaction. So I can check it by looking at the oxidized or reduced state of NAD plus or NADH, right? So I always tell the biology student, you go for the application part, try to understand the basic concept or basic logic of the technique, and you will be able to understand. So I am a specialist of flow cytometry. I am running the flow cytometry from last 9 years. So I know all the examples of flow cytometry, but I'm not that much good in the electronics of the instrument. So ultimately application is our aim. So thank you guys, thank you very much. There are some references. I found one very interesting book from Timothy Soderbergh, that is Organic Chemistry with Biological Emphasis. I am very thankful to Timothy to create a great book by keeping in mind that organic chemistry is very important for the biology student, and I have taken some online references from this link and some of the points from Leininger Principle of Biochemistry 6. So guys, thank you very much for watching my videos.